And now it is, we stay with the mergers, and I will call Andreas Bauswein to share his slides with us.
Good morning. Just a second. Can you see my slides?
We see your screen, yeah.
Do you see the title page?
No, we see all of them. So.
Okay, let me try again. Let me try this one. Now?
Now it's better. Okay.
Okay, good morning, everybody. First, I would like to thank the organizers for inviting me to give this talk. And second, I would like to stress that what I'm presenting here is collaborative work. And so I would like to point out that in particular, a PhD student of mine, Sebastian Placker, contributed a lot here to this work, and that this work was only possible through a collaboration, in particular with the Roslov group, who provided hybrid equations of state with a first order phase transition to deconfined quark matter. So what I want to discuss here is that first I want to discuss some general features of neutron star mergers and the impact of the hadron-quark phase transition on neutron star mergers. And then I want to discuss some specific aspects of first order phase transition in the equation of state. And I want to discuss which possible observable signatures such a phase transition can leave in observables of neutron star mergers. So first I will point out which impact a phase transition has on the post-merger gravitational wave signal. And I want to stress that in particular from these observations, we can even learn something about the onset density of this phase transition. And then in the second part of the talk, I want to discuss the collapse behavior and how it's affected by the presence of a phase transition to deconfined quark matter. And by collapse behavior, I simply mean the distinction between black hole formation and no black hole formation in a neutron star merger. And then finally, if I have time, I will also remark something on electromagnetic counterparts. So probably you would expect on the very first slides a phase diagram of matter, but we saw already so many. So I just put here the questions which are the main drivers for this work. And these are, does a phase transition to deconfined quark matter occur in neutron stars or at densities that we find in neutron stars? That means a few times nuclear saturation density. And if we go a little bit further, we can even ask, if there is a phase transition in neutron stars, what do we learn about the properties of this phase transition, or possibly even about the properties of quark matter? So these are the main questions that I want to address here. If we think about these questions generally in terms of neutron stars, of course, a main observable is that a phase transition can leave a kink in the mass-radius relation. And observing something like this would be a clear indication for the presence of quark matter. But there are also possibly other effects, like for instance, the presence of quark matter could have an impact on the cooling. Then if we consider more dynamical systems, it's also known that a phase transition can have an impact on the dynamics and the observables of core collapse supernovae, for instance. Here we want to focus on mergers, and here it's pretty much the same. So if there is a phase transition to deconfined quark matter, we will have an impact on the dynamics of the merger, and therefore basically on all the observables, the gravitational wave signal, the collapse behavior, and possibly also the electromagnetic counterpart. Okay, so let's speak about neutron star mergers. I show here the different stages of a neutron star merger. So I hope you can see my mouse. We start with a very long-lasting in-spiral phase. Then the merger takes place, and either we directly form a black hole torus system because the merged system is unstable towards gravitational collapse, or we form here such a neutron star merger remnant, which is mostly stabilized against the collapse by rotation. And this object can either form a rigidly rotating supermassive neutron star, or it can collapse to a black hole torus system on a somewhat longer timescale. And of course, which of these routes you take depends critically on the total binary mass and also on the equation of state of high density matter. Now here I indicated some of the messengers from these different stages. So from the very last in-spiral phase, the last 10, 20, 30 seconds or so, you can infer in particular the binary masses from the gravitational wave signal, and you can also get the so-called Tidal deformability, which describes finite size effects of neutron stars. Then in the case when you form such a neutron star remnant, as you saw here in the snapshot before, then this object will be strongly deformed, it will be oscillating, and these oscillations are very characteristic for the equation of state. The oscillations have not yet been detected in 1708-17, but it's something that should be detectable in the near future when the detectors have better sensitivity. And of course, these oscillations here are very characteristic for the equation of state in the post-merger phase. So we want to address which impact the phase transition has on neutron star mergers. And to address this, we need to perform relativistic hydrodynamical simulations, and we need to adopt equations of state. And I would like to point out that these equations of state should be temperature dependent, because in the post-merger phase, as you also saw in the talk from Matthias, you get relatively high temperature where thermal pressure can become important. And here you see an example for such a hybrid equation of state compared to a purely hadronic equation of state. This equation of state was developed by the Roslov group. As I said, it's temperature dependent. You see this first order phase transition, and if you consider here the mass radius relation, you see that this leads to a kink in the mass radius relation. And one point that I would like to make is that if we speak about signatures of a phase transition, we need to be sure that the signature of a phase transition is an unambiguous signature. That means that all other hadronic equations of state should not show this signature, because otherwise we cannot claim that such a signature would be characteristic specifically for a phase transition. So this is something important, and any signature needs to be compared to all possible other purely hadronic equations of state. Before I show you merger simulations and discuss merger results, I would like to point out one thing, and this is that detecting a phase transition by the gravitational wave in spiral phase by measuring the tidal deformability can be very challenging. You see here the tidal deformability as function of mass for these two equations of state that I showed you, and you see that even a relatively strong phase transition produces only a very weak kink here in lambda versus mass. And that means that this kink is relatively hard to measure, because lambda is also smaller at higher masses, and therefore you will have a relatively large error bar, and will be very difficult to resolve here this kink. Therefore, I want to focus on the post-merger phase of neutron star mergers, and this is only accessible by hydrodynamical simulations. And for these hydrodynamical simulations, apart from a large set of purely hadronic equations of state, I will consider different models, hybrid models with a phase transition to deconfined quark matter. You see here the equations of state, and here you see the corresponding mass radius relations which result from these different equations of state. And you see that these models really differ in, for instance, the onset density of the phase transition, the latent heat, and also the stiffness of the quark matter phase. So here you see one example of such a simulation with a hybrid equation of state. This is the rest mass density in the equatorial plane. You see here the stars before merging, they are getting deformed. Here they merge, and right after merging, essentially you form here at the highest densities and the highest temperatures a core of quark matter, and then later on a somewhat longer time scale of several milliseconds, this system slowly settles into an axisymmetric system, and you have a nice quark core here in the very center of this post-merger remnant. Here on the left-hand side, you see how the maximum density in the system evolves with time. So you have here this in-spiral phase. Here the two stars merge, and then the density increases because of the merging. The black curve is for the purely hadronic system, and here the green curve is for the system with the hybrid equation of state. And you see that it goes to higher density simply because the equation of state softens at the phase transition, and therefore you need to go to higher densities to stabilize, to get enough pressure to stabilize the object. Here on the right-hand side, you see the corresponding gravitational wave spectrum for these two simulations, so a purely hadronic equation of state and the same hadronic equation of state which undergoes a phase transition to deconfined quark matter. And what you can clearly see is that the dominant frequency of this post-merger phase is shifted towards higher frequencies. And this is somehow understandable, because if you form such a quark core in the center, it softens as the equation of state, as I argued, so it makes the remnant more compact, and the more compact remnant oscillates at higher frequencies. And this is why all these frequencies in the post-merger phase are shifted towards higher densities. So now, as I said already, a high frequency on its own may not yet be indicative of a phase transition because we want a signature which really is only produced by a phase transition and cannot be produced by hadronic equations of state. To get an unambiguous signature of a phase transition, we need to compare these simulations with simulations of purely hadronic equations of state, and the results are summarized here in this plot. So every data point here is one equation of state where I extract here the frequency of this main peak, the dominant oscillation frequency of the post-merger phase. And for every simulation, I plot this main frequency of the post-merger phase versus the tidal deformability, which is measurable during the in-spiral phase. So both of these quantities are measurable in principle, at least with some precision in the very near future. And now you see something very interesting, namely all the purely hadronic equations of state cluster here around this black line, which is just a fit to these data points, whereas the equations of state which undergo a phase transition to deconfined quark matter have a characteristically increased frequency. And that means if we measure both of these quantities, we can check whether they are compatible with this gray band or whether the post-merger frequency is increased. And if it's increased, then that would indicate or provide strong evidence for the occurrence of a phase transition during the merger phase. Let me mention that it has, as I said, this post-merger frequency has not yet been measured, but it's conceivable that in the very near future, this frequency can be measured to within a few 10 hertz or so, which has been shown by simulated injections and gravitational wave data analysis studies. So there is really hope to obtain both of these quantities and to make this comparison. Let me also mention that you see here, if you compare the different properties of these hybrid equations of state to what you see here, that there is, for instance, a clear trend, for instance, that the larger the latent heat in this phase transition, the larger is the increase of this frequency. And let me also mention that we find a similar behavior also for other binary systems. So these results here are for mergers with 2 stars of 1.35 solar masses, but we find a similar increase of the dominant post-merger frequency if we consider, for instance, asymmetric mergers or also mergers with other binary masses. And also something that I would like to point out is that we also performed some simulations with hybrid mergers, so where the phase transition occurred already before the merger with a very low onset density. And also in this case, you find a characteristic increase of the post-merger frequency. So here I summarized these results for different binary masses. So here is for 2 stars of 1.2. This is what I showed you before, 2 stars of 1.35. Here is 1.4, 1.4, and this is 1.5, 1.5. And you can see that for all these systems here, you find an increase. For the very low mass systems, you don't see yet an increase because here we do not reach the phase transition yet, or we form only a very small quark matter core, which does not affect the post-merger frequency strongly. So we don't see here a characteristic increase yet. But as you go to higher masses, the quark core becomes stronger. It affects more the stellar structure of the remnant, and therefore you get this increase. In the case of 3 solar masses, you do not see any data points for the hybrid equations of state. And this is simply because the equation of state softens and it results in a prompt collapse, and therefore you don't get such a frequency of the post-merger remnant, and you don't get any data points here. I will discuss this later in a bit more detail. As I said already, we also find such a signature for asymmetric mergers. This is summarized here. So here, if we combine the simulations of equal mass mergers and unequal mass mergers with a mass ratio different from unity, and you see even in that case you get such an increase. So we are insensitive to the actual mass ratio. And just one word on the detectability. As I mentioned already, simulated injections in LIGO noise have shown that in the near future the frequency here can be measured. So the black curve here is the injected frequency spectrum, and the shaded area here is the reconstructed, and you can see that you really can extract this frequency here. So you have a chance to really detect the signature of a phase transition in star mergers. Would like to point out one thing, and this is that, to summarize, we compare always this peak frequency versus lambda, and either they are compatible, this would mean that there is no phase transition in the merger, or we get this increase, and that would indicate a phase transition. And the interesting thing is that this also tells us something about the onset density of the phase transition, because in the merger remnant, you probe essentially the equation of state up to some certain maximum density. And that means we probe the equation of state up to this density, and it can tell us something. If we find an increase of this main frequency, it tells you that up to this maximum density, the phase transition must have already occurred. Or if I don't find an increase, then it tells you that up to this density, the phase transition did not yet occur. And the interesting thing is that we find a nice correlation between the maximum density that you find in the merger remnant versus this peak frequency in gravitational waves, which is measurable. So here you see, if I go back, again, the maximum density as function of time in these different merging binary systems, and you see that you can, for every of these systems, extract the maximum density in the system in the very early post-merger phase. And this is precisely what I plot here on the y-axis. And you see that for purely hadronic equations of state, there is a nice correlation between this maximum density that is probed by this post-merger remnant and the measurable gravitational wave frequency. And so this means that you can really put a constraint on the onset density, either if you found evidence for a phase transition, or if you didn't find evidence for a phase transition, then you can say up to this density, the phase transition did not yet occur. And just to complete this discussion, there's also a nice relation between this maximum density in the post-merger remnant and the tidal deformability. But since we anyway need to measure both of these quantities, we can use here these relations. Actually, this is a somewhat too simple picture. I don't want to go into the details here, but I indicated already that if the quark core is too small, you can in principle have the presence of quark matter without a strong impact on the post-merger gravitational wave emission. So you need to have a sizable quark core to have an impact on the post-merger frequency. But this is, of course, clear that if you have a small quark core in one system, then you just need to wait for a system with a somewhat higher mass, and you will get a quark core with a much larger size, and then you will also get a clear impact on the post-merger frequency. So the bottom line is that you can effectively capture these complications by an effective procedure to constrain the onset density. So with this, I want to slightly change the topic and speak about the collapse behavior. And as I said, what I mean by collapse behavior is simply the question whether directly after merging a black hole forms, or whether you form such a post-merger neutron star remnant. The collapse behavior is quantified by introducing a threshold binary mass. So that means if the total binary mass of the system is above the threshold binary mass, then you directly form such a black hole after merging, whereas for lower binary masses, you form such a neutron star remnant. Okay, so the collapse behavior can be quantified by this threshold binary mass. And the important point is that this threshold binary mass is in principle measurable. We discussed already that the total binary mass is measurable in an event. So we have the in-spiral, and we have for high masses a prompt collapse. For lower masses, we don't have a prompt collapse, possibly a delayed collapse. But these two outcomes can be distinguished observationally, because in this case here, for no collapse or delayed collapse, you have strong post-merger gravitational wave emission, and also the mass ejection is much stronger, and therefore the kilonova signal is much stronger. So we can measure the mass, we can check which outcome we found, and then we can say, okay, the measured mass was either above or below the threshold mass, and from this we can constrain the threshold mass. So in the future, we will have different binary events measured with different masses. We will find either evidence for a direct collapse, or we will find observational evidence for no direct collapse, and this will then constrain here the threshold mass. So the point that I want to make is that this threshold mass is measurable in the future. So now the question is, does a phase transition to deconfined quark matter leaves an impact on the collapse behavior, meaning on this threshold mass? And the answer is given here in this plot, which admittedly is a somewhat complicated plot. So let's discuss this in detail. So all the data points are different equations of state. The green ones are hybrid equations of state. The black ones are hadronic equations of state. And for all these equations of state, I determined the threshold mass, which is here shown on the x-axis. And I plot this threshold mass versus the tidal deformability at the threshold mass. So for equal mass systems, we would simply define it like this. So it's the tidal deformability of the binary system directly at the threshold. The important point is that both of these quantities are measurable because you can measure the tidal deformability. You can also infer the tidal deformability at the threshold. So we can measure this quantity with some precision, of course, and we can measure the threshold mass with some precision. So at some point, we will obtain here a point in this plot, in this diagram. And now you see something very interesting, and this is that some of these hybrid equations of state occur here in the upper left corner of this diagram, while all the hadronic equations of state occur below here, below this dashed line. And that means if we find an equation of state up here in this area of the diagram, this will provide strong evidence for the occurrence of a phase transition. This is also somehow understandable that a phase transition leads to data points in this upper corner here. The point is simply that a phase transition can lead to a destabilization of the remnant. I said already, it softens the equation of state and it produces a more compact remnant, and therefore the remnant is destabilized if a phase transition occurs. Destabilization means that the threshold mass is unexpected low. And if you have a low threshold mass, then this definition of lambda threshold also tells you that the lambda should be relatively large. As you go to a lower threshold mass, the lambda increases. So both of these effects basically push the hybrid equations of state to the upper left corner in this diagram. And this explains why they occur here in this area in the upper left corner, whereas all the hadronic equations of state lie below this dashed line. I said already that that we can possibly use electromagnetic counterparts to learn about the outcome of a neutron star merger. So the question is also whether a phase transition can leave an impact on the electromagnetic counterpart itself. So here I'm speaking about kilonova counterparts. So basically the electromagnetic transient that is produced by the radioactive decays of the rapid neutron capture process, which produces thermal or quasi-thermal emission, mostly in the optical and in the infrared. This is produced, of course, by the ejector because only unbound material can contribute to the electromagnetic counterpart. There are also different components of this ejector, dynamical mass ejection, and then you also have long-term ejection, so ejection, for instance, from a disk that is forming around the merger remnant, where matter gets unbound on longer timescales. So the question is whether phase transition can leave an impact on the mass ejection. And what you see here in the left on the left plot is the amount of unbound matter as function of time for the different hybrid equations of state that I discussed before in comparison to the purely hadronic reference model. So the hadronic reference model is shown here in black, this line here, and the colored lines are the different hybrid equations of state. And what you find here is that if there is such a hybrid equation of state, it indeed, or if there is a phase transition, it indeed leads to a different amount of ejector. For some models, it's increased. For other models, it's somewhat reduced. But the important point that I want to make is that you get some scatter, but you don't get some systematic trend if you have a phase transition in the equation of state. And here you see the ejector masses found for a larger set of equations of state, in particular purely hadronic equations of state. This shows here the ejector mass as function of the radius of 1.35 solar mass neutron star, and you see that equations of state, which are in principle very similar, can lead already to quite some scatter in the ejector mass. And you see here, for instance, that the scatter that you find here, comparing different hadronic equations of state, is of the same order as here the ejector increase or decrease if you have a phase transition. And by this, I simply want to say that a phase transition does not leave a very characteristic imprint on the mass ejection. Possibly, of course, it could lead to some more subtle effect, for instance, on the neutrino emission and on the resulting properties of the ejector, but this is still something that has to be worked out. So in principle, it will be very challenging to detect a phase transition directly from the properties of the kilonova. And with this, I'm basically at the end of my talk, so I quickly want to summarize. So what I discussed before is that if the equation of state undergoes a phase transition to deconfined quark matter, this leads to a characteristic increase of the post-merger frequency. And if you compare this to the information from the in-spiral phase, you get an unambiguous signature of the phase transition, which is simply due to the fact that the remnant compactifies and therefore leads to a frequency shift. Generally, of course, the post-merger is very interesting because it leads to higher densities in the merging system, and therefore you probe this high density regime in the post-merger phase compared to the in-spiral phase, which is more sensitive to lower densities. Then I discussed that there is a correlation between the observables in gravitational waves and the maximum density that you probe in the post-merger phase. And this correlation can be used to put a constraint on the onset density of the phase transition, depending on whether or not you find evidence for a phase transition in the merging system. And then finally, I showed you that also the collapse behavior is affected by the presence of a phase transition, and in particular, if you find a relatively low threshold mass in comparison to the tidal deformability, that this can be indicative of a phase transition. And with this, I thank you for your attention.
Thank you very much, Andy. I don't see raised hands yet, so please raise your hands if you have questions. While you are thinking, I will ask a question. Andreas, you spoke about the threshold mass for the collapse, and what is your personal opinion? Can there be a pulsar left over in our famous GW 170817?
So in principle, I would not exclude it. I mean, there has been this famous argument that if there was a pulsar, that then this would inject kinetic energy in the wind of the or in the ejector, and that the properties of the kilonova are possibly in conflict with such an additional injection of kinetic energy. Might be so. To be honest, I don't have a very strong opinion about this.
Yeah, there are some indications, but it is not yet definite that there is a kind of.
I think we need to understand I think we need to understand the mass ejection and the interpretation of kilonova much better to make here a very strong statement. This is what I basically want to say.
Okay, thank you. Now we have a question from Veronica Dexheimer.
Hi, can you go back a few slides?
To stop me?
Okay. Oh my God, maybe forward. Is the one that you show the tidal deformability threshold versus the mass threshold?
Mm-hmm. This one.
Yeah, so you have a diagonal line there.
Mm-hmm.
That's from theory?
Let me go to this plot here, which is a bit more complicated. The dashed line here is drawn by hand, just to guide the eye here, because you see that they lie here in the upper left corner. However, you see that this dashed line nearly coincides with this blue line here. What I did not discuss, not to make it too complicated, is that there is a very tight correlation between the threshold mass, lambda threshold, and the maximum mass of non-rotating neutron stars. And if I plot here sequences of constant maximum mass using this empirical relation, then you find here these blue lines here for hadronic equations of state. And in particular, this solid blue line here is the 2 solar mass constraint. And this tells you that no hadronic equation of state can lie here on the left of the solid blue line, because you cannot have an equation of state with a lower maximum mass here. It's only possible for hybrid equations of state to enter this regime. So although these equations of state are compatible with the 2 solar mass constraint, they lead to a lower threshold mass. But because of this tight relation of the threshold mass, the lambda threshold, and the maximum mass, no hadronic equation of state can go beyond this solid blue curve. Does this answer your question?
Yes, thank you.
Okay, I don't see further raised hands. Is there another question in the audience? Then I have a very short one. You showed this injected to LIGO frequency stuff, and this was injected at the frequency of 2.5 kilohertz.
Mm-hmm.
But for our signal, we have 3.5 kilohertz. So have there been similar injections been done for higher frequencies too?
Yes, yes. So this is just one example here, but actually we tested a large set of different equations of state.
Mm-hmm.
And I mean, the 3.5 is of course for this particular model of the hybrid equation of state, right? If you have, for instance, somewhat stiffer hadronic equation of state, then possibly also the shifted frequency will be at lower frequency. So it's not so clear where exactly you expect this frequency, right? This depends on the details of the model. But we also tested higher frequencies, and they can be also detected. Of course, it will be a bit more challenging because it's at higher frequencies, but it's possible.
Mm-hmm. Thank you. Then I would like that we all thank Andy once more.